Good morning. This is Dr. David A. Padgett. This is the weather and climate class, spring 2021. Today is March 4th, 2021. First thing I'm going to share my screen. The first thing I want to discuss today is the lapse rates assignment, and just looking at some of the results that were turned in. So let's just go to the assignment itself. I'm going to go to student view. And assessment, Dropbox. And so here it is, assignment 5. And so essentially you all were given the task of examining the causal factors behind there being snow in Hawaii, looking at it from a physical sciences aspect. And so you were to read this article that discusses or describes the phenomenon that occurs in Hawaii at its Mauna Kea mountain, or volcanic mountain, to be more exact. And so when you read this article, you might have been surprised to learn about how much snow, not just a little bit of snow, but how much snow falls in Hawaii. And so we used this article as the basis to formulate this exercise, looking at important topics such as the environmental lapse rate, the dry adiabatic lapse rate, the saturated adiabatic lapse rate, stability and instability in the atmosphere, precipitation, condensation, cloud formation, and orographic precipitation. So all of those concepts are inherent in this exercise. And so let's move forward and look at some of what you all turned in. So let's first look at the schematic profile turned in by Kaylee Rhodes. And so this is basically what we worked through on Tuesday together. So here we have a cross section of the mountain, or the volcanic mountain. And so she correctly here has labeled these temperatures as they have changed in a parcel of air as the prevailing winds force this parcel of air to the peak of Mauna Kea. And so we noted that the lapse rate, or atmospheric lapse rate, is the rate at which a parcel of air changes as it moves through the atmosphere. Okay, I know that's kind of an abstract concept to grasp at first, the fact that you can have air that's separate from other air, but that's exactly what happens in the atmosphere. It's called the fluid properties of air, where you have gases essentially have liquid properties in the atmosphere. So notice that, so we made note of those changes. And one of the main thing that we should note is that this parcel of air started on the windward side of this mountain range at 80 degrees Fahrenheit, as Rhodes has properly stated here. And then as it was forced over the top of the mountain, of course, it cooled as it rose higher in the Earth's atmosphere. Gravitational pull was less uh, prominent or had less of an effect upon the air mass. And then, of course, at some point we had precipitation, and then the um, air mass descended down the leeward side of the mountain range at the dry adiabatic lapse rate. So as it moves closer to the Earth's surface, the gases in the air mass compress, and of course that means they're going to warm up. And so you see, we started over here at 80 degrees Fahrenheit, wound up on the other side at 102 degrees Fahrenheit, which is a graphic illustration of the rain shadow effect. And as we mentioned on Tuesday, at the actual Mauna Kea, on the windward side, we have a tropical forest, tropical vegetation that is common or that we would expect to see in this region. And on the immediate opposite side of the mountain is a desert environment. So two very different plant and vegetative ecosystems created by this, what we call the rain shadow effect, which is among the orographic effects related to mountain ecosystems. So let's look at I'm going to use Theodora's response to the questions as the best example of what was submitted in response. And so here, in answering the various questions, I mean, we did these in class, but what I really like about what Theodora did was she actually added the calculations. And so when we get to the midterm exam next week, this is what I would like to see you do, is when you encounter a question like this on the midterm, and there will be a lapse rate question on the midterm, you're going to be asked to show your work. Exactly how did you arrive at the various answers with regard to changes in temperature within parcels of air. You're going to have to show that, not just write down an answer. And so Theodora, clearly showed exactly how she got to the various answers there. Next, I really like how Theodora answered this question. At what elevation would you first expect to see clouds form? And so, as we saw in the schematic diagram, the parcel of air started out at 80 degrees Fahrenheit. When it got to 3,000 feet above mean sea level, it reached 65 degrees Fahrenheit, which, per our knowns, is the dew point temperature for the parcel of air. Okay, and we all know that the dew point temperature is the temperature at which condensation takes place in the parcel of air or in the atmosphere. So, making note of that fact, Theodore correctly says that that's where we would expect to see clouds form. Now, that's when water vapor turns into liquid water. So clouds are made up of either liquid water droplets or ice. Clouds are not made up of water vapor. The film that forms on your mirror after you shower, that is not water vapor. That's water that has gone through the condensation process and is now on your mirror. Water vapor is invisible to the naked eye. So when it turns into a liquid, that's when we start to see clouds. So she correctly said that we would expect to see clouds form at 3,000 feet. Then she defined the dew point, and this is a very good response to that question. So very good there. Next, would the clouds form under stable, unstable, or neutral conditions? So let's go back to the schematic. So notice we were given in the instructions an ambient temperature of 78 degrees Fahrenheit. Now, the environmental lapse rate is the rate at which the atmosphere cools as we move away from the Earth's surface. So this is the air surrounding the parcel of air. So if we take 78 degrees Fahrenheit at an environmental lapse rate of minus 3 degrees Fahrenheit per 1,000 feet, then we would see a cooling of 10.5 degrees Fahrenheit. So if we start at 78 degrees Fahrenheit, Theodora correctly says that the surrounding air would be 67.5 degrees Fahrenheit at the same elevation that the parcel of air is 65 degrees Fahrenheit. Therefore, as she correctly states, the clouds would form under stable conditions because the parcel of air, being cooler than the surrounding air, would have a propensity to sink. Okay, so because it would be more dense than the surrounding air. The reason that the parcel of air is not sinking is because it's being forced upward by the prevailing winds. So as the parcel of air is resisting rising, the clouds that form are going to be those flat stratus clouds that we see in the atmosphere. So if we go here to content and to, let's see where we have trying to find the okay, here we go. Here are cloud types. So below 6,500 feet, we don't add the alto or cirro prefixes, and so we have strato cumulus. Our cumulus would be the the stratus clouds. That would be the best answer here, as Theodora has correctly answered there. So those clouds would be most closely associated with stable conditions, as opposed to unstable conditions, which means that air has a propensity to rise. That's where we would see the cumulus type clouds. And so that's exactly what Theodore answered at C, stratus clouds. Okay, at the peak of Mauna Kea, what form of precipitation would you expect to see fall? So she has, it could be freezing rain, could be sleet, could be snow, would not be hail. So hail, actually, we go back to let's see if I can find the well, you have this document. Hail forms via convectional processes in the atmosphere. And try to find, well, I think maybe this week we actually had okay, here's the hail formation process. So hail actually forms in cumulonimbus clouds, and they're usually associated with warm frontal conditions, maybe very strong convection, but not necessarily, you wouldn't necessarily have a very strong updraft of air in this situation at Mauna Kea. Uh, this type of the type of storm that creates hail is a very strong, violent storm that creates these big thunderheads that have these huge updrafts. And so that is what we would most commonly associate with the hail formation process. So, um, yeah, so Theodora correctly answered that we would expect to see perhaps freezing rain, perhaps sleet. Remember, sleet is when the water falls to earth in solid form. And a couple of weeks ago, that's what we had. We had sleet and not freezing rain. Thank goodness. Sleet falls is a solid state and just bounces off of objects. Freezing rain coats objects such as power lines and tree branches. And when you have sleet, that's what really causes huge power outages, because those tree branches break, they fall on power lines, or the weight of the ice weights down power lines themselves. And then that's when we get those huge outages. And I think that's what happened more in Texas. Here we had sleet, and so we had a nice, well, maybe not nice, but we had a coating of ice on the ground that came as a result of those balls of sleet kind of fusing together after they hit the ground, but they didn't stick to stuff. Maybe they were on your car a little bit, but it wasn't the devastating effect of freezing rain that they had in Texas. And of course, there's snow, which is what we would expect. Oh, it appears as if Theodore even calculated the ambient temperatures. So that means that we would have to go to, again, the schematic. And so we notice that after 65 degrees Fahrenheit, the dew point, the parcel of air started to cool at -3 degrees Fahrenheit per every 1,000 feet at the saturated adiabatic lapse rate. And again, what happens is when we have molecules of air that move very fast become molecules of water due to the law of the conservation of energy, or energy can neither be created nor destroyed, or the amount of energy in the universe is constant. This energy from this gas to liquid state has to go somewhere. It can't just disappear. So it is released in the form of heat. So when it rains or even snows, temperatures actually rise a little bit because of the energy that's released when we go from a gaseous form to liquid form, or even from gas to solid through sublimation. That energy is released in the form of heat, and that heat counters the rate of cooling as the parcel of air or moves through the atmosphere. So from 0 to 3,000 feet above mean sea level, the parcel of air was cooling off at -5 degrees per 1,000 feet because condensation had not yet taken place. After 3,000 feet above sea level, after condensation is taking place, and that latent heat is countering the rate of cooling, then we start to see -3 degrees Fahrenheit per 1,000 feet. And so Theodore moved forward and calculated that at the peak of the mountain, the ambient temperature is going to be 19 degrees Fahrenheit. And she correctly said that given that very low temperature of the surrounding air, that we would likely see deposition take place. In other words, we would very likely see the water vapor perhaps turn directly into a solid or ice crystals, which we call snowflakes. And so it's a very good job there. And the last question, or let's discuss the impacts that mountain ranges have upon climate. I was looking for three things here. One, obviously, the rain shadow effect. And then, so that's described in your readings. The second thing I was looking for, which was described in the readings for atmospheric dynamics at week 5, was altitudinal zonation. And so we talked about altitudinal zonation being that mountain ranges, especially very tall mountain ranges, can actually affect climate. In this example here of the Andes mountain range, you see that the climate, specifically the temperatures that are experienced or observed at these various elevations, are cooler as we go from sea level, Tierra Caliente, very hot, and that's what we would expect in the tropical region, to the Tierra Nevada, which is where we have snow-capped mountains, even in very low latitudes, such as in, Hawaii. We could have, let's take a look at perhaps, let's see, Mauna Kea, snow cap. Let's get some imagery here. Oh, very good images of Mauna Kea and the snow cap. And so I don't know if that snow cap remains there year round. I'm assuming that it does. And so we notice a very interesting juxtaposition here of palm trees. This is a perfect example of the of altitudinal zonation, where on the same day you can be standing in this very lush vegetation near the foot of Mauna Kea, and at the top, and this is in the tropical region, so it doesn't matter what time of year it is. You see snow-capped mountains, perhaps in June, July, August, where you have this very lush, very green tropical vegetation below, and various degrees of vegetation biomes as we move higher and higher, or farther away from mean sea level. Here's a Mount Everest example that really shows a very detailed description of different climate regions as we get higher in the along the sides of a mountain range. So that was the second thing that I was looking for, was the in addition to the rain shadow effect, the altitudinal zonation was the second thing that I was looking for there. So take a look at your answers to these questions and compare them to what the Adora did, and that will pretty much explain why you got the grade you got. This is a just very fine example, just a couple of things I pointed out there that the Adora might have missed. Other than that, very good work. So hopefully you all got a really good understanding of the various lapse rates, and so expect to do some math on the midterm. There will be a question related to calculating atmospheric lapse rates on the midterm exam next week. So just be ready. Okay, so this going back to sharing my screen. So the second thing that we're going to work on today, of course, is your is assignment 6, wherein you will have the opportunity to become a certified storm spotter. And so question might be, well, why do we need to have storm spotters in the first place? For one, I think in here, I found a really good graphic that describes what we call the tornado blind spot for radar. And so this is a really good diagram. So we have lots of tools. If I don't know if any of you all were able to catch the presentation last night about the 1-year anniversary of the Nashville tornadoes of 2020. Very just excellent presentation. I'm hoping to get the recording if you happen to have missed it. And it was really, really an in-depth analysis of everything that happened last year with those tornadoes, and just it was just excellent. But the one thing that came out of that presentation last night that I really found interesting was that even with all the computer models, even with all of the instrumentation, even with all the scientific innovation in weather prediction that we have at our disposal right now, the atmospheric conditions did not project, or did not, the weather, the meteorologists did not have a sense that what happened was going to happen last year. In other words, that we were going to have these very destructive killer tornadoes racing across Middle Tennessee based upon the information that they had. So that was very interesting, because there's all kinds of warning systems in place. And yet there was no, I mean, there was an expectation that there was going to be some severe storms. I'm not saying that these tornadoes came out of nowhere, but the type of atmospheric conditions that we would normally expect to see to produce that kind of tornado just were not there. So the same could be said for radar in terms of in real time. So what I'm talking about in terms of the expected or the estimated risk for tornadoes to form, the atmospheric conditions did not suggest that. Now, if we go to real time, let's take a look at some of the real-time imagery. So we go to real time. This is a screenshot I took last night. Certainly, we have instruments that can track the tornado path. Here, this was the EF3. This is the tornado that hit Tennessee State University's campus. It was an EF3, very large tornado. It was a mile wide at this point in probably western Davidson County. I think that's in Davidson County. No, excuse me. This is Lebanon. So this is Mount Juliet. So this is the one that, yeah, it was a mile wide. I'm sorry. This is after it passed through. Same tornado after it passed through Nashville. This is Lebanon. And so it was a mile wide. So that's difficult to appreciate. And the tornado was moving at 50 to 60 miles per hour and a mile wide with, let's see, EF3, EF3 well over 100 mile per hour winds. But let's look at some of the issues associated with, or some of the limitations of the technology with regard to keeping us safe. So yes, we have radar. Yes, we can watch these tornadoes move through our neighborhoods in real time. But even with the radar, as you can see, radar shoots out straight away from the radar station. The Earth's surface is curved. And so as you can see, it's very easy for a tornado to hide here in what's called the radar gap. In other words, the radar can't see it. And so that's why we need to have storm spotters on the ground to call in to the National Weather Service. The National Weather Service then in turn calls the reports to the news stations that broadcast out warnings and for the impending or possible approach of tornadoes. So that's how that system works. Still need human eyes on the ground. So let's go to your mission. And so, okay, so normally what we would do and what we have done for several years is the local National Weather Service office would send someone to TSU and actually be in our class, and we would go through the storm spotter training in class. At the end of the class, you would be a certified storm spotter, not a storm chaser, storm spotter. So you have several options for becoming a storm spotter. You only have to do one of them, okay? You can go to the Skywarn spotter site and complete step 2, and step 3, okay? And then read the instructions. I mean, if you want to go forward and register with the spotter network, you can. I'm only asking that you do 1, 2, and 3, but you can move forward. Don't worry about being a cert volunteer at this time. So that one, just provide evidence that you completed each step. Like I said, at some point, you might be issued a certificate. If there was some assessment or exam that you took and they gave you some results, please provide that, either the screenshot, just provide some evidence that you actually completed the training. Okay, that's fine. Now, if you want to become an official storm spotter, then there might be a couple of extra things that you need to do. All these are different. Or you can go to the Memphis storm spotter training. Now these are webinars, and they're given at man, wait a minute. Let me stop the recording right now. Just give me a second. I'm sorry.